This lesson is about polynomials and division. Let's start with this example. If we were going to divide these polynomials, the procedure would be a lot like that which you learned in elementary school for basic division of numbers. So I'm going to guide you through a four-step process here that we'll have to do repeatedly in order to do this long division problem. Before we start, the denominator or divisor goes on the outside of your division. Okay. Step one, I like to call divide leading terms. That means you take the leading terms of each polynomial and you divide them and ask yourself, what is x to the fifth divided by x squared? But let me state that another way. We want to find something that when multiplied by x squared equals x to the fifth. In other words, green times green has to be pink. Well, the only way to achieve that is to put an x cubed here, because x cubed times x squared is x to the fifth. That's our first step. Second step, I like to call the multiply step, where you essentially multiply the term you placed on the top times the outside or the divisor. Essentially, we do the blue times the blue. And in order to do that, we use our basic distributive property. So the x cubed multiplies by both of the terms on the outside, yielding this. Step three, I like to call changing signs. It's essentially the subtraction step, where you change the signs on the polynomial that you had just written after step two. Pay close attention to the plus sign that's half black and half red. Keep an eye out for those in this video. The multicolored plus sign is there to remind you that while this term used to be negative, it got changed into a positive during the changing sign step. And step four is called the combine like terms step, where you take any terms inside the division that are alike and combine them. Now the end result of that step here is this. Let me explain. The x to the fifth and negative x to the fifth are like terms and opposites as well, so they cancel. Now as far as all the other terms under the division symbol, there are no other like terms. So in the combine like terms step, everything carries down, and now I proceed. Okay, now that I've done with those four steps, I get to do those four steps all over again. And you keep repeating these four steps until something happens, and we'll get to that later. But let's go back to step one, the divide leading terms. But this time, we have different leading terms because we use the bottom row or the end of the last step as the beginning of these four steps again. So just like before, we want to use guess and check or any other form of cleverness so that you can fill in the top of the division problem. In other words, green times green has to equal pink. And after a little thought, you realize the only way that can happen is if I put a 4x on top, because now you can see green times green does equal pink. Step two is the multiply step, where we take the answer from step one and multiply it by both terms on the outside of the division. In other words, doing blue times blue gives me this. Step three, change the signs. Once again, notice the plus sign that's half red and half black. Step four, combining like terms gives us this. I'll explain the details. First, the x cubed terms are alike, but since they're opposites, they cancel. And furthermore, these two terms are alike, and they combine to make the 17x. The other terms didn't have any like pairings, so they got carried down. And now I've gone through this process twice. Well, we're going to go through it a third time. Step 1, divide leading terms. Once again, we need to fill in the box so that green times green equals pink. This is mostly a guessing type of situation. The only thing that would work, as you can see here, is a -5. That's the only way green times green can be pink. Step 2, multiply. Multiplying my answer to step 1 times the outside, in other words, multiplying blue times blue, gives me that. Step 3, changing the signs. And step 4, combining like terms. This is the result for combining like terms. Here's why. The x squared terms are alike, and because they're opposite signs, they cancel. But these two terms are also alike and combine to make -22. The 17x didn't have anything to combine with, so I carried that down. Now, you've seen me go through the 4 steps 3 times. And the question now becomes, when do we stop? Why don't we go through these steps one more time, or enough time after that? Essentially, here's what determines whether you stop. Stop whenever the degree of the bottom, which you have at the end row, is less than the degree of the divisor. The degree of the bottom is 1. Remember, degree means highest exponent. Since we have a 17x to the 1 here, of course we don't write the 1. That's a first degree polynomial. But notice the divisor is a second degree polynomial. So once the degree on the bottom gets lower than the degree of the divisor, you stop. And if that seemed a little confusing to you, you'll probably know when to stop anyways. Notice the following. If we tried to go on to step 1 again and go through this process a 4th time, we would be asking ourselves the same question: how can green times green equal pink? But as you can see in the current situation, that wouldn't be possible at all. Unless, of course, we went into something weird like negative exponents, which we don't traditionally do on division problems. And you'll sort of get a sense of when you should stop, but generally it's when you can't go any further. Now let me give you some vocabulary associated with this division process. This thing on the bottom we call the remainder. That shouldn't sound unfamiliar to you, just like elementary school mathematics. As I mentioned earlier, this on the outside is called the divisor. And this polynomial on the top is called the quotient. Okay, great. Well, that's what everything's called. But where's the answer in all this mess? Is the answer the remainder? Is it the divisor? Or is it the quotient? Well, it turns out it's a mixture of all 3. You see, the final answer to a long division problem always has this format: quotient plus remainder over divisor. Now, if this seems strange, it should vaguely remind you of elementary school math. Remember problems like this? Whether you do or not, when you would do a problem like this in elementary school, you would often write 7 2/5 as the answer. You maybe didn't put the plus sign in there, but you essentially were saying 7 plus 2/5. And that should serve as a reminder that this format, this quotient plus remainder over divisor format, really isn't anything new. Moving on, now that I know the quotient, remainder, and divisor, I simply plug those into the format, and that is the answer to your division problem. Let's look at another example. The denominator, being the divisor, goes on the outside of the division, and let's run through those 4 steps multiple times here until we get to a good stopping point. Step 1, divide the leading terms. The only thing that could go in the green box is x squared, so now green times green is pink. Step 2, multiply. Notice the blue boxes. Step 3, change signs. This is basically our subtraction step. And step 4, combine like terms. Here's the result, and here's what happened. The x cubes canceled because they were opposites. And furthermore, these two terms were both x squared, and they combined together to make the minus 5x squared. The other terms, the 4x and the minus 7, carried down since they had no like pairings to combine with. And back to step 1. Step 1, we ask ourselves, notice the colored boxes, what times x equals negative 5x squared? The only way that can happen is if I put a negative 5x in that box. Step 2, multiply. Step 3, change signs. And here's the result of my combining like terms step. Notice the 5x squared's canceled, and these two terms combine together to make 14x. Let's go through our steps again. Step 1, green times green equals pink, or the divide leading term step. Well, the only way that that can work is if I put a positive 14 here. Step 2, multiply. Step 3, change signs. And this time when I combine like terms, the lead terms cancel. By the way, that should always be the case if you didn't already notice. And the remaining terms combine together to make negative 35. So just as before, the degree of this, which is 0 by the way, because it has no variables at all, is less than the degree of this, which is 1, because of our x to the 1. And that lets us know when to stop. But again, if you're a little confused on the when to stop thing in terms of the degrees, which is a little strange, you can avoid all that and let common sense be your guide. Suppose you tried to go through these 4 steps again. Well, when you got to the green times green equals pink step, what could you possibly put into the green box times x? That would be negative 35. Without going into negative exponents or other weird constructs, that's not even doable. So you get a sense when to stop even without knowing the official rule. But now that we're done, we have our usual vocabulary. That's the remainder, that's the divisor, and that's the quotient. But none of these in isolation is the final answer. The final answer is quotient plus remainder over divisor. And filling all those in, I've got my final answer. The process you've seen twice now is called long division. I'd like to change the subject now to a different way to divide polynomials called synthetic division. Here's an example. Now, this problem looks no different than the ones we've done in the prior 2 examples. And you could in fact use long division on this. But I'd like to show you what some people consider a shortcut and others consider messy algebra. And I'll let you be the judge of whether this is a shortcut that you want to engage in or not. But here's what you do on synthetic division. Actually, before I get started, I have to warn you that what you're about to see is the end result of decades of mathematical research. It's the result of tons of trial and error and just weird different shortcuts that mathematicians have tried over the years, so it's going to look a little strange. But it is something that is a shortcut if you can train yourself to get used to how counterintuitive it is. But here's a discovery that was made. After years of research, someone and a group of people probably discovered that if you take the coefficients out of the top, there's my constant coefficient, there's my linear coefficient, There's my quadratic coefficient. And if you take the coefficients out of the top, sort of strip away the variables, we can make a really nice shortcut that will lead to the answer to this division problem. Now the next coefficient would correspond to an x cubed term if I have one. Notice I have a 4th degree term and a 2nd degree term, but no 3rd degree term here. So in my synthetic division, I'm going to put sort of a 0 placeholder here to represent the absence of an x cubed term in the numerator. And finally, the coefficient in front of this x to the 4th, which is blank, is considered a 1 for algebra purposes. So the discovery was this. You can take the coefficients out of the numerator, leave the variables aside, and set up the process that will lead us to the answer. Now what you've got here is a line and a box, and you'll see what purposes those serve here in a minute. In the box, we'll go a -3 in this case, which, by the way, is always the opposite of this number here. So the opposite of +3 is -3. So here's the discovery. The first thing that you do is you bring down whatever the first number is. In this case, it's a 1. Next, you multiply that number by the number in the box. Notice the two things in red. I'm going to multiply those together. Red times red, -3. And you put that in the next column. Then you add that column. Notice what's in green here. Adding the numbers in green gives me -3. Now, I haven't finished this process, and you can already see how nonsensical it is. It's amazing that human beings spent decades devising this shortcut. But as strange as it seems, if properly trained, you can use this shortcut and will probably grow to prefer it to the long division process. All right, the process continues. Every time you add a column and get the result, you multiply that result by the corner number. So red times red, -3 times -3, +9. And you continue along in the same fashion. Adding the column, and then multiplying that result by the number in the corner. -3 times 5, -15. And the process continues. Adding the next column, and then multiplying that result by the corner. Ending with the addition of the last column. So that's the process. But the one thing you'll notice in this whole process is there isn't a single x anywhere to be seen. This process was designed to take the letters out and make it a purely numerical process. But of course, the answer to this division problem should have x's all over the place, as we saw in the previous two examples. Ultimately, we have to write our answer in the same format, quotient plus remainder over divisor. But this process raises an interesting question. Where's the quotient, where's the remainder, and where's the divisor? Well, of course, the divisor is always the denominator of the original problem. That's easy. Now, it turns out the discovery was made that this last number, whatever the lower right corner number in your synthetic division process is, that number is always the remainder. So that's easy to find. What's not so easy to find is the quotient. Here's why. The quotient comes from these numbers, but it isn't literally just those numbers, because of course the quotient should have x's in it. Here's how to reinsert the variables that we stripped away in the first place. Whatever your last number of your quotient is, that's your 0-degree term or your constant term. So that's going to be part of the quotient. It'll be the last term of the quotient. Working my way from right to left, the next term is my 1st-degree term. 1st degree meaning the coefficient of the x to the 1st power. So that 5 really represents a 5x term in my quotient. And as we go right to left, the degree gets higher. Now I'm on to my 2nd-degree term, meaning that's the coefficient of x to the 2nd. Next would be my 3rd-degree coefficient, the coefficient of x to the 3rd. And if I had more numbers, there would be a 4th degree, 5th degree, and so on. Now that I've reinserted the variables, it turns out the quotient is the sum of those terms. Now that we have a clearer image of what the quotient is, we can piece the quotient, the remainder, and the divisor all together into our final answer, just like we did in the long division process. Having seen two processes for division, it would be natural to ask, when do I use long division and when do I use synthetic division? Long division has no restrictions. You're never required to do synthetic division if that's not a shortcut that you like. Long division will work on any problem, whereas synthetic division has a restriction. The shortcut only works when you have a linear divisor. Let me clarify. In this first example, one would have to do long division because you have a quadratic denominator and that's your only option. For the other three problems, because all three denominators are linear, meaning they all have x to the 1st as their highest exponent, all three of those problems are eligible for synthetic division. Again, not that you have to use it, because long division is doable on those problems as well. But they are eligible for the synthetic division shortcut. Me personally though, because of this 4 here, when the x has a visible coefficient, other than the invisible 1, it makes the shortcut more cumbersome and actually turns out, in my opinion, not to be a shortcut. I didn't even show an example of that in the video because it's not recommended by me. When I have a coefficient in front of x, even though I am synthetic division eligible, I will often use long division because I find it actually faster that way. So in summary, long division can be used on all problems, but I recommend when your denominator is x plus a number or x minus a number, you might find the synthetic division shortcut worth your while. And that completes the lesson.